parallel dazu, dass ihr das auch nochmal vielleicht vor der Prüfung dann entsprechend anschauen könnt. Okay, so welcome everybody to today's lecture on implant-associated technologies in orthopedics, and we will be focusing on device development today. So I will present to you a device that I developed during my time doing the PhD here, and at the meantime try to teach you one or some of the skills that are required for doing so. Okay, I see. This is a bit annoying with the video, but I hope you can manage. So today's agenda will be focusing on some of the main points here. So first of all, we will be looking at which kind of methodology should we follow on how to develop medical devices? Is it different to classical technical devices in a way? How do we identify medical problems and solutions in that manner? Then actually the main part of the lecture will try to teach you some stuff about what is required for device development. So we'll be focusing on some kind of mechanical CAD design or just recapture a bit. Then we're going to take a closer look at embedded systems, meaning we're going to look at microcontrollers, then how can we do something useful with microcontrollers? So what kind of sensors do we need? What kind of output devices? Then we will be looking at the serial communication to tell the sensor or the output device from the microcontroller what to do. And finally, how do we, in which kind of manner do we program everything up? And to conclude, I would, if I have the time, show you some examples that we did at our laboratory. Okay, so the main question of today is how do we design a system that actually is capable of harmonizing with the living system as well. And for that, we will be focusing on one particular part of methodology that we will be looking upon. I guess you guys already are familiar with it a bit, but we're just going to take a look at the Münchner Vorgehensmodell or Munich procedure model from the medical point of view. So here on the left, we have the medical side, and that's the most important side we should be very thorough about and we should be starting with. So when we get some kind of problem, we first should talk to a doctor. We need to define what kind of target we want to plan. Then we really need to spend some time in analyzing that target. If we are capable of really analyzing that target thoroughly, we can start to structure our problem. And then here the interconnection between medical and technical side is then to find a solution that is capable of mitigating between medical and technical side. So to do that, we need to identify the main characteristics of our problem. Then somehow at some point we need to make central decisions. And finally, we need to make sure that we are capable of reaching our targets in the final stage. So these, you can see here, all these graph nodes are interconnected. So this can be a process where we can be repeating all of these steps. So just to give you an example, we're going to be looking at this from a very practical example from our lab and try to just follow the methodological steps that we want to obtain along the way with the Munich procedure model. So here, I would just need to tell you a bit about what this was about. So this is for so-called CRPS patients. That's called for chronic regional pain syndrome. So that's very specific to our case here, not too important to remember in general, but just to give you an idea. So this disease or this syndrome appears for patients that had a very bad fracture, for example, of their limb. So here we will be focusing on the human hand. And if they had a bad fracture of their limb, they will need to perform some kind of rehabilitation process. What is the problem for that patients? That's one thing where I did talk a lot with the medical doctors. They gave me that information. They gave me their practical experience. So I was asking them a lot of questions on that stage to really try to understand the issue. And one of the main things they told me is that the rehabilitation is very difficult to do because it requires a lot of time. The problem is the patient does not want to move the hand because it's very painful for the patient to keep moving the hand, and we need to find solutions on how to motivate that patient in doing the rehabilitation. So we want to support that rehabilitation process. We want to somehow semi-automate this recovery, and then finally bring back the full kinematic functionality of the human hand. One problem is that the stiffness of that hand tends to increase, so it's really difficult for the patient to keep moving that hand. So that's in the planning stage, and what we then agreed upon with the medical doctors is to actually finally try to design a robotic assistive device for the human hand. So that's what the goal of that planning phase was. What do we actually want in the first place? Okay, let's keep following along that path here. So next, we need to thoroughly analyze that target. So here, I can go a bit faster about this. We want to understand the healthy system that we will be looking upon. So here, it's the human hand. So as an example, we should be able to define the kinematics, axis of rotation, what is all affected, and for example, also the range of motion of each of the finger joints, if we want to design something that can then actually be used to help that patient. So as an example here, you can see the respective flexion, extension, or abduction angle of that human hand. That is all part of this analysis target process. Okay, also part of analyzing the target is further understanding the pathological system that we see here. So we don't have healthy patients. That's also nice if we can develop an exoskeleton that's really fine for healthy patients. But here we focus on this kind of special symptoms. So what do the patients have? Again, gathering information from the doctor and research. Here in that case, reduction of range of motion. We have an increased stiffness. The hand is really hypersensitive, etc. And then we can also try to cluster that, so we can see maybe some of these effects that we see from the disease do actually really have, for example, direct effects on the kinematics. So for example, the reduced range of motion will of course lead to an effect on the kinematic chain. In this case, actually, it's maybe also helping us a bit because the decreased range of motion does not require the exoskeleton in the end to be completely operational and as powerful as it might be for a healthy patient, because we might not need the full range of motion during the therapy in the first place. So just to give you an example, maybe we can also simplify from that stage. And yeah, then of course something like swelling, temperature, color changes that are also indirect requirements that we need to be dealing with. Okay, so next in the stage is still in analyzing the target. So now we understand the hand, we understand what the pathological symptoms are, but we also need to pay attention to the environment that we want to deploy our system in. So in this case, we want to use this exoskeleton to be supporting in physiotherapy. So if we can help in supporting physiotherapy, then we need to maybe pay also close attention. What are the requirements then for this exoskeleton? So one really effective thing, again, talking to the doctor, they told us what they do in therapy, and maybe ideas for replacing or supporting therapy here is the so-called mirror therapy. So you put a mirror on the one side of the hand, and then the patient will look on his actually healthy hand and think that he's moving the healthy hand by looking at the mirror. What helps him to move the hand because he has a real high aversion against the diseased hand. So that's just an example that the doctors tell us this is one requirement or one really nice scenario that we would like the patient to use. So what does that mean for us? Maybe something like doing a game where we can see the hand just on a screen, so not be looking or not having to look at the diseased hand in the first place. Okay, next we need to follow again the path here. We should then do the requirement engineering part. So what kind of requirements are now really being focused on for our system. So we need to structure the problem in such a way that they capture the desired features and constraints of such a system. One way of doing that is using the so-called SMART principle, just to highlight that one here. So try to be on these requirements very specific. Then these requirements should be somehow measurable, so it should be something that is in a way a bit concrete. You can now really grasp what is going on. Then, of course, you want to actually be able to fulfill the requirements, so don't be too ambitious on that stage. And of course, also realizable in the way, and you want to keep everything in time limits. So if you want to have requirements that may be affected in 3, 4, 5 years, you should maybe not do this for a PhD project, because you might be already gone when you actually achieve your specific requirements. Okay, then we can really structure all these requirements, and we should of course classify all these requirements as well. So one thing we should do is, what should the device really shall do, what is really required in the first place, what is critical, and other things that you might only should want to have. So they are nice to have in a way. And then once you have all of these requirements really formalized, you can look at all of the available systems. For example, there you do your literature research, you look at the respective requirements or the respective technical solutions that are existing already, and you try to find out systems that might be suitable for you. So how can you approach that in a more sophisticated manner? You can look at the pros and cons for each of the respective system, and then based on this, you can finally decide on which systems you should prefer, or which system might find a good match, and which system should be already excluded at that stage. So you can really narrow down your solutions in this stage already. Okay, so this is also the part where you then, just to recapture here the words, bring about your decisions. Cannot really jump back in this presentation mode. Okay. And then finally, you want to reach the targets that you attained. So in this stage, you should really pay attention to what kind of risks are there in your project, which kind of shortcomings might you have in terms of finding maybe the technical solutions, but also in terms of testing everything finally. So will you be able, for example, to have patients available to you that you can work with, that you can test the system with? Are there maybe delivery times that you should consider if you want to, for example, buy a special motor or a special sensor? So pay attention to the respective risks that can help your project in failing, and look at how you can avoid them. Maybe take a motor that is not that shorted, or already communicate with the doctors in an earlier stage to find proper testing. Okay, and so one takeaway for your own development projects is, what can you also do to identify some of these problems? And we will try to list some example applications here. So if you have your own projects available, maybe one good process of how you might get started here in general is study the anatomics of the respective limb that you're working on. So try to get as much knowledge about the respective limb as possible. Are you working on the hand, the shoulder, the knee, etc., or the ear or something? So try to get really familiarized with that respective problem. Then, of course, might be something useful, use magnification methods. That is dependent on your problem, of course. But if you're working, for example, with cochlear implants or something, you might look at things a bit different or on a different scale than if you're just working on the human knee. Then you want to gather more information. Something like X-rays will give you a lot of information about the respective bones that are included. Or if you use an MRI, you get more information about the functional tissue, so the tendons and muscles that are included in your respective human body system that you will be looking upon. Of course, you can always get things a bit more complex. So how do things look like in 3D? The MRI gives you already an idea about this, but also you can use a CT or an MRI to really get a more holistic picture of everything that you want to do the research about. And then finally, one of the most important part is always try to keep an expert about the respective disease and the respective limb close by. So ideally, you have the luxury of talking to a doctor. We have that here, of course, at the university hospital, but that's one of the main parts where your projects gather a real chance for success, because you might exclude a lot of wrong paths already with talking to the expert. So just to list some of the example applications now that you can be looking upon for your research or your respective projects. There are a multitude of medical devices. This is, of course, something like cochlear implants, hearing aids, glasses, exoprosthetics, but of course also for the implant devices, endoprosthetics, some stents for example, the heart, then of course something like crazy like cell-free tissue matrices, or if you go into the surgery, for example, minimally invasive surgery, these are of course also medical devices that you want to optimize. And if you exactly know the respective limitations, where they are being applied, what kind of workspace you have available, this will of course be central to your design requirements. So to summarize, the analysis and the understanding of the underlying functions of the biological system are the basis for every medical technologies approach. So this is more or less the main part to really the medical side of things. Now we will be a bit more focusing upon the actual device development. So to get started with that, and we will first be looking, of course, on the CAD designs, computer-aided designs. For that, there are a multitude of solutions that you can, of course, be using. Nowadays, Onshape is getting a bit of traction, but CATIA and SolidWorks are also great solutions here. So just in general, using any of these solutions is great. So be very clear about all of your components. And then one of the main part is try to generate your assemblies. So you can really know how do all of your components interact with one another. And for that, finally, for any kind of manufacturing, you can, of course, then generate your output. But during these assembly constructions, you can already check for collisions in your system. You can further intensify the kinematic analysis, and of course, finally generate your current bill of materials. So what do you actually need? In this stage will always be somehow interconnected with the next stage, where you will then define your circuitry. Because, for example, for some scenarios, you might need to use respective platine somewhere, and this one will also take some workspace and maybe change your CAD design. So if you have both open, or you keep a close talk with the respective engineer that is doing the PCB design part or the MCU part, where you design the electrical part of things, and the more classical mechanical part, your project is prone to much more success or much less errors during the development process. Then next we will be talking about this actually embedded system. So what do we actually want? We want a system that is defined by some kind of CAD design that will help us. For example, the exoskeleton, we have our kinematic structures, we have everything more or less set up, how we want everything to be designed, but of course we also want to interact in the end with the patient, or we want to measure something from the patient. We want to objectify in this case, the rehabilitation process. And for that, we need some kind of measurement of the environment. So we need something like sensors, and we also might need to interact with our environment, like using an actuator or something that can really give the patient some feedback or display something on a screen. All this is then connected with some logic, the electrical hardware, the embedded system as a final solution. Now this embedded system can of course be interconnected to other embedded systems. So maybe you have a multitude of exoskeletons, or you have some external sensors that are also interconnected to that one, or you access everything via a wireless communication, something like, or something more general with the internet or another mobile device. And in doing so, we can a bit classify all of these embedded systems. First of all, in terms of their general complexity. So how sophisticated is your respective controller? So is it only 16-bit, 32-bit, 64-bit, where nowadays actually the focus is on the 64-bit controllers. And then you can see here how is the general architecture. Is it a standalone system? Is it real-time capable? Are you interconnecting it with some other networks as well, or maybe some also mobile system that is appended to your local exoskeletons, for example, or your local embedded system? So nowadays, on the left side, usually we have 64-bit, and on the right side, there are a lot of mixed forms available. And usually one good thing to follow is to somehow trying to generate something that is then interconnected to something like a mobile phone, because the applications get much more simple in programming and developing on that side. Okay, so now we can take a closer look a bit on the electrical part of things. So one of the central things of an electric or an embedded system is the so-called microcontroller, that then via external circuitry is to connect it to some kind of sensors or the actual outputs. So what we try to a bit further understand right now is how does some of these microcontrollers work, what are their maybe limitations, what are their advantages, to just get a bit of a better understanding of these controllers. So in general, a microcontroller is a very small and efficient computer, and it has a single integrated circuit in it. And usually it's just a single chip, as we can see one example of such a microcontroller here on the left, and it contains multiple things. So a lot of people think a microcontroller is just a central processing unit, a CPU, which just handles all the calculations, but that is not really sufficient, because there are much more things required to make a CPU a sophisticated microcontroller. We're going to see that in a second. You need memory, you need input-output accesses, etc. So a microcontroller is not just a microprocessor, and a microprocessor only has that CPU part, but a microcontroller is much more advanced. And in placing such microcontrollers on a general scheme, we have multiple strategies of doing so. So one thing you might classically know is something like Arduino. So this is actually from the class of development boards. So this is a single microcontroller here on that respective development board, and it has additional external circuitry, something like a boot reset and some decoupling capacitors. So that means if there's some voltages appearing for the microcontroller, this one ensures that this microcontroller will not be destroyed via these decoupling capacitors. So that's a very simple and basic board, and the main thing is you have a lot of in and output pins that you can access this microcontroller with to later on connect some sensors. Next part is a single board computer. This is something known like a Raspberry Pi. So it's already a complete operating system, and it has much more input slots. And finally, we have the system on chip design. This is something that's a bit more new. This is something like Apple uses, and here's the example of the M2 chip. So just to rephrase a bit, the microcontroller, the main thing is we have the general input-output ports, and we can very simply write some simple user programs upon this one, and for example, use software like VS Code plus Platform IO will get you started with any kind of microcontroller very fast and write your respective simple software for that respective part. And of course, you can see here it's not that large, so maybe for an embedded device for medical developments, it's a good way of getting started, because you don't have a lot of overhead on the system. Then something more sophisticated, a single board computer like a Raspberry Pi is just an extension of everything. It's a bit more focused on actually being a complete computer. So you have an HDMI port, you have much more access, it's also much more powerful, but of course it also is just a bit larger. So maybe for some devices also already a bit of an overshoot. And then the final thing just to be mentioned is just how nowadays systems are sometimes being constructed by just chaining all these respective chips together, and this system on chip design can have a multitude of single microcontrollers that interact with each other directly on a single chip. But now let's try to understand a bit more about that microcontroller from the first part. So as I already mentioned, microcontroller is not just a CPU, there's much more to it. But of course, the central part of the microcontroller is the CPU. But just an extension to that CPU, that's actually the main thing that's calculating some kind of results. We have, for example, some watchdog timers here. So they just check for the respective tabs. So which kind of processes should the CPU perform right now? And one thing also quite important, we have some interrupts here in this central part that allow us to actually, if there's something safety critical, might be also important for medical devices, we can directly interrupt everything we're doing right now, every calculation we're doing, and directly handle that immediate threat in a way and prioritize that part first. Then we have the memory part of things. So that's also very important. If we have no memory, we cannot really do a lot. And there are different kind of memories we have available. There's, for example, the main part, the program memory, and the flash, or the flash. This is where you write your own software and you write it on that part. So it's a non-volatile memory. That means if you turn down the system and you turn it up again, the memory is maintained. The EEPROM is also non-volatile, but it's just a lower lifespan, so it's a cheap solution for also having more memory available in a way. And then there's the RAM, the random access memory. That's the one that is actually volatile. That means if you shut down the system and you turn it on again, all the memory on that part is lost. But it's very handy for just accessing things during runtime. Next, we have, unfortunately, my head's in the way, but here we have you can see it here on the left, the respective resets. So there is the power on reset, where you can just click. So this is the general application that is being run if you just power the system. That's a normal state that it's going to be using. Then there is the brown out reset. That means if you lose voltage, so there's something, you lose the circuit, you shut down the system, there should be a kind of routine that is applied if you shut down that system. So to not set the system in some very unknown states, once the voltage is dropped below a threshold, this reset is triggered and just more or less handles as controlled shutdown. Then you have external reset, which you sometimes need if the system is, if you broke the system in a way or it's running in some unknown application, then you can really externally reset everything. And then one of the main important parts here is the general input and output pins. So this is where we will be accessing all our external sensors with. So this is one of the main advantages of such a microcontroller. Next, there are lots of things happening in this single microcontroller unit. We also have the timers. So they allow us to, for example, follow certain frequencies where we have an exact clock being set from these timers, and we can then actually manage our external sensors with that respective clock signal. So we have a frequency on which we want our signals of the sensor to appear. And for these timers to be very exact, usually some development boards such as an Arduino have external oscillators. So they get an input signal from such an external oscillator. It's mainly just a sinusoidal wave that is being generated from some clear mechanical defined system. So it's just running on that certain frequency and very exact about this. And this gives more or less the input for some of the clock signals. So it is really exactly timed. There's also an RC oscillator, so that's one that produces a really stable sine wave internally. And then there's some special things like a phased locked loop. So this is also a voltage-driven oscillator, and this one can really adjust to match external frequencies. So if you get an input signal with some frequency that you do not know, you can use that phased lock loop, and it will then try to let the system run on that external frequency. Okay, then next things are communication protocols. There are a multitude available. We will be talking today about SPI, I2C, and UART, so I will mention them in a bit more detail later. For serial communication, so a kind of strategy of how can we actually communicate with our external sensors. And one other thing I'd like to mention here is the analog to digital converters. So some of the sensors signals that we obtain just deliver us an analog signal, and we want to somehow perform or convert it to a digital signal to be actually able to work with that one and process it with the chip itself. So why is all of that important? Why should we know about all of these microcontrollers and their respective structure? Well, one thing is that these microcontrollers really are a very cost efficient and real-time capable solution nowadays. And yeah, they are commonly used as a classic embedded system. And one thing that's really nice about them is that they really use the resources available very efficiently, so you can really maximize or design your microcontroller system in a way that is operating for exact the amount of requirements that you need. So you don't need to set up a big PC next to you. You can just put this very small microcontroller there on your device, maybe directly, and you have all the logics that are mainly required in reading the sensors and doing all the main logic of handling things on that very small chip. And that's why we should also be looking a bit on what kind of sensors we can get, because now, again, to medical devices, of course, we want to somehow be able to read what is going on, which kind of sensors are available to us. So what are sensors in general? Just to repeat that, devices that detect and respond to input from the physical environment are these sensors. And we have different kind of sensors. So for one, we have the analog sensors. Maybe that's the classical part. So they're the first one. They just measure real stuff from the physical environment by being affected by that physical environment. So they are very fast. They're not bound to any kind of frequency, as it just happens. They just are affected by the environment, and they're also not in any kind affected to a certain range of, for example, the digital input, or how many bits of resolution do I have available. But they also come with a lot of bottlenecks. One thing is that because they are affected by any kind of physical disturbance, they will also transmit that respectively. So if you have a very long wire length connected to one of those analog sensors, then everything that is happening on that wire will also affect the signal. And a lot of them will require you to use external circuitry, so this will require you to further deal with these signals. So for example, this analog sensor here, FlexiForce, it is made for measuring force signals. And this one usually, if you supply it with 5 volts, it will output you a signal in the millivolt range. So that's very hard for the microcontroller to deal, or for the ADC converter to deal with only millivolts, because it usually expects a range of what the microcontroller has available, so maybe from 0 to 3.3 volt. So if he only gets millivolts, that's a very sensitive signal to be used in general. So you might to amplify that signal. We're going to look a bit at that later to gather more information here. And then on the other side, we have the digital sensors. So they're quite nice because they already provide you with everything you need. You already get the digital input of your sensor. So you don't need to really handle all this conversion and what is actually going on. Often they have an internal logic already, and you can look on the data sheet at exactly what the signal will tell you here. Then further, as it's digitized, so it's just ones and zero already, you don't experience these losses as before with wire length changes, etc. So they're also not so susceptible to drift. So the longer the wire, the more the voltage is altered. But of course, we are bound to a certain frequency, and you may require additional controllers to handle what these kind of signals should be doing. So let's take a close example of some of these analog sensors. Here from left to right, just to visualize some of them. Left you have a pressure sensor, then here you have a light sensor. Here this is a rotary precision sensor, and you can always see this are between 2 to 3 pins that are used for each of these sensors, and in a way they look quite similar. This is then here on the bottom a temperature sensor, a Hall sensor for measuring a magnetic field, and here on the right a FlexiForce sensor. And in all of these systems, the main idea is we want to actually measure some kind of voltage change, because the environment will change the resistance of one of these sensors, and this will then in the end lead to a change in the voltage. Some example, if you want to, for example, measure an angle, we have a multitude of solutions available to us, and then we also at our product design stage need to choose or make the decision, to remember that part again, which kind of sensor should we choose and why. And here, just to name some example, here's for example the rotary position sensor. This is a magnetic field sensor that can indirectly measure also angles, and here on the right you can also measure it via some kind of flexion that is applied on a system, so that this can also be corresponding to an angle. So you have a multitude of solutions available, and you might need to choose which one is suitable for you. So for example, for something like the exoskeleton system that we talked about earlier, maybe something very simple here is already sufficient, and we don't need to get things more complex. So that's one thing to focus upon. But of course, in general, there is no best solution in picking the right sensor, and try to use the sensor according to your, choose it always according to your application, optimize it for that part. And of course, using the respective sensor might also require you to use or to extend your requirements in an additional manner. If you use a very complex sensor, then you might have to pay here more attention, or maybe a very too simple sensor that might then actually not fulfill the resolution that you picked in the first place. So just to give you some more intuition about how these sensors are generally working, we can look at a general potentiometer here. So this one will in the end deliver you the angle or output. Finally, the output you will get is the angle of that respective potentiometer. How is that one positioned? And the way this is done on the physical stage is that you have an input signal, an output signal, here a voltage in between, and you run along a resistive strip with this kind of wiper. And the further you move along that strip, the higher, for example, the respective resistance increases. So that is just an example on how the resistance changes by using this. And this in the end is working similarly to a voltage divider. So if you pick in between here your output voltage, you will see that this output voltages tend to change depending on the resistances you use here. And this is according to this respective formula. So let's just try to follow along this formula for one thing. So we can again try to remember one of the most basic formulas in electrical engineering, which is V equals to R times I. And if we look at the left side here, we can see that V in, okay, I'm writing really bad, is R1 plus R2 times I. And on the right side, we have the same, but only with R2. So V sorry for that, out equals to R2 times I. So if we want to solve everything for V out here on that left side, you can see my draw, we can just solve that one for I. So I equals to R1 plus R2 this is in brackets, divided by the out, V in, sorry. Or am I miscalculating here a bit? And then we can replace that part in here, so we get the wrong formula. So who can help me here in solving that part for a second? So we have the two resistances, and that should be, so V in equals to this part, solving it for I, we divide by R1 plus R2, and that's here the error. So maybe I can write it on the formula, or try to write it above. So I equals to V out, V in is written in here, divided by R1 plus R2. So sorry for that. And then we can input this part in here, and then we can directly see that V out equals to R2 divided by R1 plus R2 times V in. And that's the formula we see on the right. Sorry for my bad writing, so I got confused a bit, because this is probably not the most practical part of writing formulas with the mouse. Okay, just to give you a basic example, this is affected by the respective resistances. And then, of course, what do we need to pay attention to in the end? For one thing, we need to somehow map between the respective resistances to our actual output angle. So that part is the calibration part. How does our actually output voltage change over the resistance, and how does the resistance change over the respective angle? So if we can solve for that, we know our correlation between the angle and the output voltages, and that is our calibration step in this respective part. Then of course we need to pay a bit of attention to the sensitivity. So how is this whole system being affected by certain voltage ranges? Do they change, etc.? Finally, of course, the environment also will affect the respective sensor readouts. So maybe temperature or humidity can play a big role here. Then some of the respective sensors might have a lot of noise. So you might need to respectively filter those. So for example, a force sensor is a very high frequency signal, and you can filter the respective signal using, for example, a resistor and a capacitor that will then help as a low pass filter. We heard about the low pass filter in the robotics lecture already. So high frequency signals will then be filtered, but also something like the cable length, respective shielding from, for example, other magnetic devices plays a role. Are you using proper grounding, etc. All these things should be paid attention, closer attention to if you use these analog sensors. Then we can switch a bit to the digital sensors. So here again showing some of them that are available. So for example, an inertial measurement unit here is a complete digital sensor, and that's already producing the required output that you might need, or the respective sensor outputs in a digital manner. Then you have time of flight sensors. You see they all look a bit more complex than the one before. So the analog sensors usually 3 pins, and the moment you see a lot of pins, you might already have a digital sensor that is then a bit more sophisticated already. But again, same as for the analog sensors before. So if you want to choose one of those digital sensors, pay close attention to what kind of sensor you need, what are its advantages, what are its drawbacks, If you look at a website, something like Mouser, you will see a multitude of sensors that are proposed to you for one specific scenario, and you will then, that's where the engineering part comes in, need to read a bit on the datasheet what kind of limitations that does the respective sensor has, and which one should you choose for your application. Then, of course, also some things to pay attention to with the digital sensors. So one thing is some sensors might need to perform their calibration on startup. So if we, for example, look at an inertial measurement sensor, that is very specific in that case, this one will measure the orientation in 3D space. But one of the problems is once it's powered up, it doesn't know to which respective frame it should express its orientation. So in that manner, it needs to somehow find, for example, first of all, gravity, so orientate itself downward in a way, and then a classical way is to try to orientate yourself along the magnetic field, so north, try to point north maybe, so that would then lead to two axes being defined, and the third axis follows along the right-hand rule, so you would then know your position of your inertial measurement unit. So this can be required for some sensors, that you need to calibrate them each time you start up the system. Further, of course, also these digital sensors are affected by environmental factors, because underlying are some physical effects that are being cleverly measured and then digitized in a way in the first place. So of course, again, environment factors matter. Also, sample frequency, for example, are things that might limit your design. So maybe a certain sensor is very high performant and very accurate, but it can only give you a solution every 2 seconds. So then this sensor might not be suitable for a real-time application where you want to really control, for example, the motion of a finger or something. And maybe some of the respective sensors have proper limitations in terms of their power supply or the reference voltages they need. So you also need to pay attention and read what kind of input voltage do these sensors need. Usually they offer a range, but sometimes your microcontroller only has 3.3 volt and this one starts only at 5 volt. So you need to pay attention if you can actually fulfill the sensor requirements here. And then finally, we can also talk a bit about the output devices. So now we talked about on how we can measure things using digital and analog sensors. But of course, we would also like in the end to then give feedback, for example, or output something. And this one we can do with, for example, external monitors, or the classical thing, the most recommended one is if you have an actuator, you want to, of course, control that actuator in a certain manner, or for example, something simple like outputting sound. And again, these can be split into analog and digital. And just to go over that one a bit briefly, so an analog output device, something like an analog motor, brushless DC motor, for example, these controllers in the first place might also need additional controllers. So if you are, for example, trying to plug in directly a brushless DC motor, you might get into a bit of more tedious work, because you then need to really design a complete motor control scheme as an external circuitry. So you need to pay attention on how far you want to go here. And there are solutions in a way that are a bit simpler to use, as we're going to see in a second. So all of these systems often will require you to use additional external circuitry. A bit more simpler are the digital output devices, because those you can usually control with something like a PWM signal, a pulse width modulation signal. We're going to see a bit more about those in a second. But usually the idea is you can just apply the range that you want to, the torque range or the general range of that motor via one single simple digital signal. And one thing you should pay attention to, something like these motors, you might need to require separate power lines to control these signals. So if your microcontroller is working on 3.3 volt again, it's not maybe sufficient to power a very powerful motor, right? So you need to plug in the motor externally to an additional power source here, and that you should also know about. And finally, just some takeaways about these output devices. You should already decide upon which output devices you are using when you are more or less formalizing your requirements. So maybe you need some certain force ranges you need determined from the stiffness of, for example, your hand. You might need already, or you might already know which kind of motor is suitable here. And then for the classical way, I think until like 3-4 years ago, what was very classic, you had external monitors of each of your embedded system. Of course, they're heavy, they need lots of signals to be connected to be able to display something useful. So one recommendation I would highlight is nowadays, it's actually really nice to just focus on then communicating the information of this microcontroller via Bluetooth or wireless communication outside to an external device. So something like that is already available, a mobile phone, can then be used to display everything you want to display in the first place. So you don't have to put everything on that little embedded device to show all the stages there. So the headless operation is then easily possible, and usually it does not come with a lot of restrictions. Only you need some kind of Bluetooth antenna integrated into your system, and then you're actually ready to go. Some examples on external circuits that might be required for your system to operate properly are, for example, an external voltage divider, if, for example, you need different voltage ranges that you want to operate upon, or something more classical is an amplifier. So maybe you get a system. I had just this problem from 2 weeks ago when we designed a new force sensor. And this, for example, this force sensor has again only the range of 3 millivolts. Again, the system wants to read something like in the range of 2 volts. So we need a huge amplification of the respective signal. And for that, we need a lot of external circuitry just to get that single signal here, or the single signal for one, also supplied, and then scaled up respectively with all this circuitry to then scale it up to a 3-volt signal in the end. This will then be sent to analog to digital converter, and this will then be much more easy to interpret finally. Okay, so now we have more or less a bit of an understanding about the microcontroller, some restrictions about the sensors, and of course also the output devices. Now it's time to try to connect everything together. Well, how do we actually try to communicate with our motors and our sensors? So a very pragmatic solution for communicating, for example, with our motors or displaying some status from an LED is to use PWM. So it's called pulse width modulation, and the idea actually is quite simple. You simply define a duty cycle, so this is the whole time of that respective duty cycle, and then you set your PWM signal to be active for a certain amount of time within that cycle. So for here, first example, you have an activity of 50%, here for example 75% activity, or here 25%, and you can then alter that as you need respectively. And what then the actual motor or the output device will be doing in the end, this is how it's often solved, is for example your servo motor will then be active for this amount of time with maximum torque, and then being shut down for the rest of the time. But because the frequency is so high, that will appear to you or to the output of the actual motor to be an operating of 50% of the output torque in a way. So this is an easy and simple way to communicate with your respective output system and to tell it what it should do and how much force it should use by simply using a single data signal and then just modulating this respective PWM signal. So some examples are servos are operated that way, PC fans, a lot of LED signals, so the intensity of a LED light is also affected by such simple ideas. So we keep the light 50% of time on and then off, and then it will on average appear for the human eye as being not so bright, for example, or even something like your oven at home. Next, so this is how you can communicate with, for example, your actuators. Then there's also very important part about the serial communication. I mentioned that already earlier a bit, that for example, we wanted to focus on I2C, SPI and UART. So that is what we will be focusing upon now. The main idea in serial communication is to send data 1 bit at a time. So in series, send it out all after the other. And so this is not a parallel communication. You don't send everything at once. And then you might have a lot of problems in interpreting which bit is actually doing what. So you send everything in series, so you know exactly at which address should which bit arrive. And this communication can be synchronous or asynchronous. We will see two synchronous examples, one asynchronous example right now. And usually this whole thing that we want to connect to is a serial bus. So a bus connects to multiple devices and allows data transfer between these respective devices in the end. So let's now look at, first of all, the I2C communication strategy. So this is integrated circuit. This is very handy because it only requires you to use 2 wires for the communication. Are you also using only 2 wires to connect your external sensor to? No, usually you always connected the external sensor also to your 3.3 volts, so your VCC, the operating voltage, and your ground. But then additionally, you only require the SCL and the SDA signal. So the SCL signal is the clock, the system clock, and the SDA is the system data. And this is a very simple communication scheme. Once the first of all the data is pulled low, then the clock will start. We can see that here, running on all of the respective systems, and then the master can, for example, first of all communicate what he wants to happen. So first of all, he will communicate to some kind of slave with a respective address. So he will send on that data line to all of the respective slaves out, this is the address I want to communicate to, and I want to, for example, read or write on that address. So classical way, reading sensors, we want to read. And then this respective sensor has received its address and knows, okay, I want to read or write, so it will acknowledge that process. Then the actual slave, so the sensor, will send its data. And once it's done, it will again send, the master will send its acknowledgement. And this can continue for a lot of time, but finally, once everything is happy, we can then finally stop our signals again and pull them up to high again. So that's the basic idea. So only one slave can communicate at a time, right? But it's a very simple process because we only need 2 data lines and we can access as many simple sensors here as we want to. A different idea is to use the SPI, so the serial peripheral interface. So here we need a lot more signals. So we don't just use the clock, we had that one before already, but now the data signals are here separated into MOSI and MISO. So MOSI is master out, slave in. So this is only the data line that is actually used by the master to send out stuff to the respective slaves. And then the slaves all use that shared data line of MISO. So master in, slave out. So this is the one that the slaves use, or the sensors in a way use to send data to the microprocessor in the end. And further, before we had some kind of strategy. So we first send an address to which slave do we want to communicate to. Here the strategy is a bit different on which slave is selected via this further additional pin called slave select. And this one is pulled low for the respective slave that should then send the data. So this is the basic idea. But of course you can see there are a lot of signals being required for this setup. So not only do we have an additional signal for the data, but we also have for each sensor unit a single signal being used right here. There are solutions that use so-called daisy chains, so they then go from the first slave to the second, so they try to then again be a bit closer to I2C, but that also reduces the speed of this system. So the main advantage of this system is that in the end the communication can be much faster than with the previous one. And then also a very simple system that is more or less the classical one that is not being used that much anymore nowadays is using UART, so Universal Asynchronous Receiver Transmitter. So here this is asynchronous, all the other signals were synchronous. The main idea was we always had the system clock that determined when do we want to send signals. Here we do not have this part, but this again comes with some additional requirements. If we do not know the respective other system time, we need to already set everything in advance. So if both systems know that they should operate at a very certain frequency, then this communication can work, but you need to predetermine that in advance. But then the actual communication is again quite simple. The only thing you need to really pay attention to is to send the transmission with the receiver end of the sensor and the transmission end of the sensor to then the receiver end of your final microcontroller. So this is one thing to pay close attention to. And then usually you have a very simple communication scheme. Unfortunately, my head is again in the way, but you can hopefully see it on the slides. The idea is to simply send the data after some time, and then you again switch to the idle position and you stop. So you send a start bit, then the data, and then finally right here where my head is, there's a stop bit. Okay. So let's look a bit closer to the respective communication schemes and their advantages and disadvantages as a summary. So for I2C, this is really nice. We had only 2 additional signals we had to use per sensor. So you also should keep that in mind, because if you have a microcontroller and you're using lots of sensors, then maybe this might be a good way for you to go, because you might then somehow get limited with your general input-output pins. So you only have maybe 15 pins available on your board, and you have 20 sensors, so you might already try to think about a solution that is rather in the range of I2C or SPI, right? Because for UART you need 2 pins for each sensor. It's very simple in a way, but it is limited to one device. So here I2C, multiple devices, only 2 wires, and everything is synchronous. So it's quite easy to ensure that the data integrity is correct. This is of course maybe also here a bit limiting. If you don't have the correct synchronization, you don't match the times and you don't match everything, so UART might be a disadvantage here. But of course, one of the things that is limiting, for example, I2C, is it's only meant for short distances, and in comparison to SPI, it's comparable low speed. So it's limited in terms of the width or the bandwidth you can send over the respective signal lines. And here, the use of using more signal lines comes with the benefit of having a higher data transfer speed, but of course, on average, you just need a lot of many more pins than compared to the I2C setup. So you need more pins to get started, and then you need 1 additional pin for each further sensor that you use. So, of course, that is not all that is there available. So I2C, SPI, and UART are just some examples of serial communication. Of course, there's also USB, Type 2, Type 3, Type C, etc. So there are different kinds of USB data transfer strategies. Of course, there's also Ethernet. You can communicate via Bluetooth or Wi-Fi, or something also different, for example, optimized for different input signals, for example, for a monitor, VGA or HDMI, are also strategies that you can follow. So now, once you have everything set up, so you have all your sensors, you have your microcontroller connected. Now it's part for writing some kind of software on the whole system. For that, it's also good to know what kind of different softwares are available to you. So first of all, the main thing that is on your chip is the bootloader. So this one is stored in the non-volatile memory, of course. So it's very fixed, and it just manages what the system should do on power on or on reset. So it just manages that very initialization part of your chip. So it performs the initialization of the embedded system, and then it will, once it's done, it will hand on everything that it has performed, or the chip architecture, to the actual control application in the end. And the control application is the firmware. This is the custom written code that actually then gets finally executed. So that is what you will maybe be writing in your Arduino project or otherwise. So the simple software that will try to then, or hopefully, or at least sufficient software that will try to then perform everything you need to do with your embedded system. So common languages here are C++, but there are also two different Python solutions now, MicroPython and CircuitPython. But since there's ChatGPT as a support tool in writing software available nowadays, I think it's the best performant to then write your software using C or C++. Now, there are different kinds of architectural designs on how you could write your respective software. So one thing that you might have already heard of is the way Arduino does it. So it's a quite simple idea. You have the super loop. So first of all, you run your initialization loop. So you set this kind of sensor I want to communicate to with this baud rate, and I want to use this kind of communication strategy, etc. And I want to initialize that sensor. And once everything is done, you just run your main loop where you have some kind of main logic in that loop. So for example, read all the sensor signals at the start, and then perform some kind of logic, some kind of calculation, and then, for example, put that respective power on the motor. So we're gonna set the PWM signal of the servo motor to a respective value. But of course, depending on your application, there can be different solutions in doing so. So one other example is maybe also using interrupt-driven device. So this is a bit more security critical. So maybe some of your sensors will tell you there is a very important event happening. So maybe your force sensor you have connected to your device tells you you have surpassed some threshold. So maybe now you're starting to hurt the patient because you're applying too much force. Then it's very critical to actually react in real time. So for that scenarios, maybe an interrupt-driven software architecture is much better. So where you then directly, if you remember, you have those watchdog timers connected to your CPU. So you can directly go in there, break everything that is happening right now, all the calculation that the system is doing, and say, okay, this has priority. We have that interrupt. There is that respective event that happened, and we will now perform this respective routine to avoid some kind of danger or security risk for the patient. So that's the interrupt-driven design. Then also a design that is maybe also quite handy for a bit more complex signals or complex programs is to operate on so-called state machines. So the idea here is if you just keep making your main loop here in running in the first place more and more and more complex, this is all one giant loop and everything is happening all at once, it might be a bit difficult to understand what your system is actually doing now because it goes through a crazy amount of things. And if you do something, for example, you want to connect your system to a Bluetooth, and then your external application will send commands via Bluetooth, and you will then operate depending on those commands. Maybe it's smarter to use a so-called state machine. So where the different states could be, for example, we are searching for external Bluetooth devices. We are now connected to a Bluetooth device, and we have started a measurement, or we will now be operating in a certain mode of that measurement. So the state machines can be a very handy thing, and it's just for making the code a bit more understandable and for other users to be able to support your system or to understand what is going on. And then depending on what you're going to be using, maybe also something like a scheduler-based system is a good idea. So the main thing here is you have maybe a long system or a long measurement that's going to be running. And for example, every day at midnight, you want to perform some certain critical measurements. So this will then be something nice for a scheduler-based architecture where you have different measurements at very predefined times that should be executed at this time. And for the rest of the time, you maybe want a system to save a lot of energy, so not be running through the main loop for 20,000 times per second, but then to just be resting and not doing anything, but then every day you turn on, do the required stuff, and then you turn off again. So that's a scheduler-based system. Then finally, also just in general, some guidelines for prototyping with these embedded systems. Some takeaways that I can really highly recommend is when you get started with these projects, you're often highly motivated. You're like, okay, I want to get the new super duper design and want to get the best motor and the best sensors together. But you might not do yourself a favor in that way, because in general, you should always try to keep it as simple as possible. Because if you over complicate things, if you add too many sensors that you actually have no really use for, your system gets a more bulky. Also, the requirements are increased because all these different new sensors might require you to use extra pins or extra voltage supplies, and your system just blows up. So try to keep things as simple as possible. So the complexity to a minimum. Something that is really nice if you can somehow easily, I would call this, debug what is actually happening in your system. So maybe you have a status LED or some kind of clever way of informing yourself about the respective system states. If you, for example, use something like an external mobile application, once everything is figured out with the mobile application, you can then, of course, easily extend this debug process by displaying lots of values of your interest here. But in general, it's a good idea to also keep that on the low level. Some LEDs that would just tell you that everything is set up correctly is already very, very helpful. Okay, then something here, execute decentralized commands. So the main idea is here to keep your commands that you want to operate upon in a way a bit more simple. So maybe write a driver in the first place that manages everything for you in the required manner. So for example, if you have a motor, maybe in the end, what you want to actually be setting in your main code is just position that motor at a very certain position or at a certain force that is being applied from the force sensor, etc. And you don't want to have everything being managed also in the main code where you then start to set this kind of torque, or we set this kind of voltage now, because then this will have these and these consequences. So try to keep everything a bit more structured. So then in your main code, this will then just be a simple line, motor dot perform 3 newtons, etc. Okay, then of course it's really nice if you have everything together, everything set up, whatever system you want or you need, into some kind of nice environment, so it can be much more easily integrated with what you want to be using in the end. Okay, and with that, for the very last part of this lecture, just very briefly, I want to quickly just go over some of the projects that I had personal experience with and what were the certain requirements that I chose and why. So one system I developed was, for example, an inertial measurement based system with 5 different IMUs. The goal was to measure the human gait in this case. So yeah, IMUs were the best way to go here. Then how do we display everything? How do we calibrate everything? Here the main idea was to simply use a mobile application where we can then go through different stages of calibration and then also the visualization and data collection at once. So here I would recommend to use a headless system, and just a simple LED was used to display for each of the IMUs if they are properly working and happy with what they're doing. Then as mentioned before, for example, also the exoskeleton system, and we did that for a DFG grant for CRPS, as I mentioned previously. So here just the example for the single finger, and the final solution that we designed. And we wanted to measure all the respective finger angles and know all the forces and torques in that system. And the way we designed everything was to use just these simple kinematic links. And then for measuring the position of the fingers, we had these rotary position sensors. You saw them before already. So it's a very pragmatic solution, as these sensors are quite simple. And then how did we apply forces? This was a linear actuator based on a servo. So we only had to send a single PWM signal here. And then how do we measure all the forces in the respective system? There was something special for the CAD design. But what we figured out was that this whole system is a linkage structure. So by knowing the external forces applied here, so if we measure here, we can then solve for the whole system and solve for all the respective linkage forces within each of those rods. So that was the basic idea. And then we know not only the position of the exoskeleton via the position sensors, but also the forces in these rods as well. So it's a bit more pragmatic in a way, I would at least say, because we can measure the whole position of the finger with only 3 potentiometers and a single force sensor here at the back and a single actuator we can use to then actuate everything. So it's in a way a bit pragmatic, but it serves its purpose. And we don't need, for example, 3 or 4 motors for actuating the finger, because just moving the finger for those CRPS patients is already sufficient. How is then the system circuitry designed? For example, here, very important, we have those force sensors. And I mentioned previously, we then need these amplifiers, because only millivolts need to be then scaled to volts. So we need amplifiers here. Then these are analog signals, so we need to send them to the analog to digital converters. Same with the 3 potentiometers, also these sensors are analog sensors. And then we have our central processing unit here within that microcontroller chip. And finally, we can actuate our motor with the PWM signal and send out our data here with the Bluetooth connection. And once we have all the data sent out with the Bluetooth connection and can receive commands with that Bluetooth connection, we can also do something funny like these little games that then I designed upon the system, so we can not only measure where the system is at each point in time, but we can also then use that to perform some kind of gamification during the therapy. Or here we used the force input of the system, so applying forces on the system can then accelerate this little orange dot, and then this can, for example, be used to play some games during therapy where you try to collect these little rod dots and try to avoid the rectangles. So it's a bit of a gamification process during the therapy using this existing exoskeleton system. So again, using here a headerless device for us was very beneficial, because we only had to make sure we have this Bluetooth connection running, and then we could solve everything on the mobile side. Okay, so with that, I'd like to thank you guys very much for your attention today. So next lecture will be after Christmas on the 13th of January, again in lecture hall C. So this was an exception today. And yeah, don't forget to also still vote for the exam day if you haven't already. Okay, with that, Merry Christmas, Happy New Year. Hope to see you guys in the next year.